So while Mark's getting set up. So we've heard from Sophia about all the tools that you can use to break smart contracts and the research that can be and will be applied to this area. One thing that we'd like to do is give you a preview of what some of this academic research can do. So for the last few months, Mark has worked on the Manticore project at Trail of Bits. It's a dynamic binary instrumentation tool that primarily uses technologies like symbolic execution to gain introspection into these kinds of programs. So we have ported this tool over to use the EVM bytecode format. So it has a whole Ethereum virtual machine shoved in there that we can use to evaluate what the outputs of possible inputs would be. So if you want to really invest the time to understand what you can do with a smart contract, how you could audit it, or how you could subvert the trust of one of these contracts, then what you might want to do is you might want to look at Manticore. I will string this along while they're So I'll say Manticore is an open source project from Trail of Bits. We open sourced it back in April of this year. We offer bug bounties for it. If any of you after this talk go home, and Ethersplay as well. So Sophia really drilled into Ethersplay. Any tool that's on the Trail of Bits GitHub is eligible for bug bounties from us, up to $200 a bug. We give those out every single point release that we make. So if I owe you any, if you've made pull requests to Trail of Bits repos, just come contact me. I'll give you some cash for the bar tonight. But Manticore is definitely eligible for that. We've been really lucky to have lots of community engagement with this. This release cycle is going to end on December 22nd. We'll make a new release just for Christmas. And it's going to include a huge number of community contributions that people have made. And all those people are going to get an extra little couple dollars in their stocking come around Christmas time. So with that, so you should really pay attention to some of the things that Mark's got to say, because this stuff might be useful for you if you're going to audit more contracts. And we'd love to have your participation in our community. So Mark, tell us about automating your bug finding on the blockchain.
Check, check. Hey, Dan, thanks a lot for that intro. Hey, everyone. My name is Mark Mossberg. I'm an engineer at Trail of Bits, and I work on program analysis software. Today, my talk is on automatic bug finding for the blockchain. So I'm here today to talk about a project I work on called Manticore, which you've heard a little bit about tonight. It's a tool that can analyze computer programs, recently including Ethereum smart contracts. It actually works directly on binaries or bytecode. And so it doesn't analyze like Solidity. It actually directly analyzes EVM bytecode. It can do a couple pretty cool things with smart contracts. Manticore can automatically discover all the functions in a contract if given the bytecode. It can generate sequences of transactions that drive the contract into unique states, including failure states. And it can check if those paths it found were actually failure cases, such as assertion failures or other security issues like integer overflows, unchecked external call, stuff like that. So the rest of this talk is basically going to be describing the technology behind how Manticore can do these things. And so we'll start off with describing in general the key program analysis technique that Manticore uses, which is called symbolic execution. Symbolic execution is a program analysis technique that lets us automatically reason about code and write tools and robots that can find bugs for us. And so let's begin. So first, let's quickly review how concrete execution works, because it's useful to contrast. This is a really simple pseudocode program that gets some input and then performs some assignments. At every state in the program, these variables have a specific numerical value. And so if the user entered in 42, A would have 43 and B would be 0. They're all just concrete regular numbers. Under symbolic execution, one thing is different in that variables are no longer required to actually have a specific numerical value. They can actually represent ranges of values. And so in this way, variables in symbolic execution are more akin to variables from algebra, actually. So if we symbolically execute this code, x, since it comes from user input, will be set to an unconstrained symbolic variable from any representing any number in the range int min to int max. Next, a, since it depends on x, will also become a symbolic variable. And lastly, b will be a regular concrete variable, since it's simply assigned to 0. This shows how symbolic variables can propagate throughout a program. Things get really interesting when we consider what happens with control flow in symbolic execution. In this code snippet, we have an if statement that is based on user input. And so the var variable is going to be first an unconstrained symbolic variable, any number in the range int min to int max. But then when we hit this if statement, it's unclear what to actually do. Var is any number, so it seems like execution can go both ways here. So what actually happens in symbolic execution is execution does in fact go both ways. The symbolic execution engine implementing the analysis makes a copy of itself. In one copy, it explores one path, and the other copy explores the other. In order to do this, it needs to record the path constraints necessary to make that path satisfiable. And so in order to explore the first path, the var variable is going to transition from an unconstrained integer to a completely constrained integer to the variable 42, because that's what the semantics of this if statement require. Conversely, in the other path, var will be constrained to anything but 42. This is a really fundamental part of symbolic execution, and is why this kind of analysis can get extremely good code coverage. And this is the heart of how the analysis systematically explores code. This is a lot, we'll go through it slowly. This is a more worked through example of how a piece of code, what happens when some code will get symbolically executed. It's a very classic symbolic execution example taken from some other slides from the University of Maryland. But basically, it visualizes what happens when we symbolically execute the code on the left. The code on the left has 3 input variables, A, B, and C, and 3 concrete variables, X, Y, and Z. The code has some control flow based on the user input, and sets the concrete variables based on the user input. At the end, there's an assertion that requires that the sum of X, Y, and Z must not be equal to 3. What the diagram on the right displays is the state forking that happens when this code is explored. So every branch in the tree represents a state fork because of an if statement based on symbolic input. And it shows that there are actually 5 ways to execute through this program. Symbolic execution fully enumerates the state space of a piece of code, and it shows that it can identify one actual possible path to trigger this assertion violation, and that's with this particular path through the program here. If A is false, B is less than 5, and C is true, the assignments will be such that the assertion will fail. Along the way, the symbolic execution engine will collect all the constraints for each particular path through the program. Those are very useful because you can combine them with a constraint solver and do things like actually generate inputs that will drive the program down that path in a real execution. You can also do things like query for satisfiability and reason about the program in other specific ways. So this is going to wrap up the little whirlwind tour of symbolic execution, but the main takeaways are that using it, we can test many paths through a program simultaneously and have a method of systematically analyzing new program code. Using the path constraints that we harvested, we can also prove properties about programs in general, such as whether it's possible to violate an assertion. Now we'll use this knowledge about symbolic execution in general and apply it back to Ethereum. The key concept here is that Manticore is a Ethereum virtual machine that can process symbolic transactions. So what is a symbolic transaction? Well, a concrete transaction is like so. It's just your everyday run-of-the-mill Ethereum transaction where you have one blockchain state and you have one transaction which has a value and a data. Those are the input parameters basically. And then you have one output state. Under a symbolic execution model, a symbolic transaction is simply one where those input fields of the transaction become symbolic. And so we have our initial blockchain state. We process this symbolic transaction with a symbolic value, which means it's just a symbolic 256-bit integer, and a symbolic data field, which means it's just a symbolic buffer of bytes. This is going to result in not one, but any number of output states based on how the smart contract executed and what state forking happens when that transaction is processed. So I just want to point out here those symbolic fields in the transaction. As well, note that in the output states, the balances of the accounts actually become symbolic because remember, we didn't have a specific number in the transaction field, and so we subtracted and added a symbolic balance to the original state. So now let's go through these three things I talked about earlier and actually go into some more detail about how Manticore can achieve them. Discovering all functions in a contract, generating transactions that enumerate the state of the contract, and checking for failure cases in the contract. We'll start off with automatically discovering all the functions. This is a Ethereum smart contract written in Solidity. And the first thing that comes to mind when you think about how to symbolically execute it is, well, where do you start, really? It's not entirely obvious or intuitive where to actually begin, just looking from the Solidity level. So we have our constructor function. Well, obviously, we need to execute that to set up the proper state of the contract. And we have our regular functions, but that's what we're trying to discover. So where do we actually start? Well, in the realm of normal symbolic execution on regular programs, for example, a Linux ELF binary, there's this concept of the entry point of the binary, which is specified by the header of the file and just contains the virtual address of the first instruction that should be executed in the program. Let's try to take that concept and look at it from the Ethereum standpoint. And so for this, we need to actually look into the Ethereum runtime bytecode format. Maybe there's an equivalent entry point concept there. And so we're luckily, the bytecode format is actually incredibly simple in Ethereum and contains a number of sections, but there's just this implicit entry point at offset 0 in the bytecode because there's actually just no file header or anything like that. The main sections in the structure of the bytecode are as follows. There is a dispatch stub at the start, followed just by the code of the functions themselves. Dispatch stub is just a name I made up. I don't think this is really documented anywhere, actually. But basically, the dispatch stub is the first code that executes by the virtual machine when you run a transaction. And all it does is parses the transaction data field, takes the first 4 bytes out, and checks to see whether those bytes correspond to a function ID for any of the following functions. If they don't match any of the function IDs for the functions, it rejects the transaction. The rest are just simple sequences of bytecode implementing the functions. Let's dive a little bit deeper into the dispatch stub. Just want to quickly shout out Binary Ninja also. I really love using it for looking at bytecode in disassembly. And also, if this is your first time looking at disassembly, don't be scared. It's actually easier than it looks. And the key trick to remember is if you don't know what something is, just skip it. And so let's just walk through it slowly. We know the purpose of the dispatch stub. It parses the transaction data and dispatches to various functions. And so we can see there's a call data load instruction right there. So it's clearly accessing the data of the transaction. Here we can see that it's pushing this 4-byte value onto the stack and doing this EQ instruction with a jump to offset 46. And so that's actually the first function identifier. And so that's dispatching to the first function and jumping to that offset in bytecode if the first 4 bytes of your data matched that ID. There is an identical construct right below, which checks for the second function identifier and jumps at offset hex 58 if you matched that. And I didn't mention this, but this is a dispatcher for a contract with 2 functions. And so what's left after that? Well, this is the end of the dispatch stub. If we didn't match either of those function IDs, we hit this revert instruction at the end, and the transaction reverts. And so what happened here? If we symbolically execute this code, we're going to find all paths to it, right? Well, luckily for us, all paths through this code lead to all the functions in the contract. And so if we find all the paths through it, we've actually found all the functions in the contract. So that's the first one. Now let's proceed to transaction generation. How does Manticore generate unique sequences of transactions that drive the contract into different states? For this, I'm going to be using this Solidity contract to illustrate this point. It's a small contract that has one int overflow bug here at the bottom. You need to issue 2 transactions to actually exploit or trigger this bug because there is some state it has there with this did init flag. So first, you need to execute the function once with any input, which will set the flag to 1. And then after you do that, you can enter in another transaction, which will actually reach the code at the bottom, including the unsafe code. And so this will require 2 transactions to reach the overflow, but it's okay because Manticore can detect this anyway. And so this is that first check on the flag, and then overflow is down here because we have one input argument, which is an integer, and that could be int max. And so when this line adds 1 to it, that could overflow. This is a visualization of what's going to happen when Manticore processes the smart contract. It starts out here on the left with the initial blockchain state, and then it runs one symbolic transaction. It's going to execute the dispatch stub and produce a couple other states. One of those states is going to be the revert state, where we missed the function identifier for the proper function. And one state will solve for the proper function identifier to trigger execution of that function. When it reaches this state up at the top right here, when it reaches this state right here, it's going to execute that function the first time, which is going to set the flag to 1. Now the contract is in a state where we can do another transaction to trigger the bug. So here we detect that we don't have complete code coverage of the function yet because we haven't found those two that code at the bottom of the function, and so we issue another symbolic transaction, and again create 2 more states. This corresponds to that if statement at the bottom of the function. For reference, it checks if the input argument is less than 42, and if so, does nothing. Otherwise, it does this add 1 operation, which could have the overflow. And so these 2 states are what is illustrated right here. One will be safe, one will have an overflow. So now let's go through and we break it down and look at what the symbolic values are and what the constraints are going to be. And so for this one path through the contract, and you can really think of these different paths as actual like blockchain hard forks, because they're different transaction sequences. And so in this path, we have 2 symbolic inputs. It's very simple, just from this one transaction, we have a symbolic value and symbolic data. In order to get this point, there's one constraint, and that's that the first 4 bytes must not be equal to leet. I forgot to mention that, but just pretend that the function identifier for this function here is leet. And so if it is wheat, we're going to go to that other path. And so it can be anything else than that. That's the only constraint on this path. Moving next. So this path corresponds to the safe execution path where there was no overflow. To reach this point, we need to first trigger the first execution of the function. And so for that, the constraint is transaction one's data must be wheat to get to the function. Then we need to execute the function a second time. And so the second transaction's data must also be wheat to get there. Lastly, the first argument of that function must be less than 42 because that was the constraint in the if statement. And lastly, to trigger the overflow, here are constraints. Very similar to the last one, we need to trigger the function both times. So that's why the function ID is both wheat here. And then for this one, anything, any argument that's greater than or equal to 42 will trigger that path. And so now let's actually make it concrete. So we can take those constraints and feed them to a constraint solver to actually generate concrete inputs that we can send on the blockchain. And so for this first case, for path one, the revert path, the only condition is that the transaction's data was not wheat. And so Z3, which is a popular constraint solver, might return something like this. The value is unconstrained, so it's just this random 5,000 value, for example. And the data could start with cafe, because that's not wheat. And so that'll be fine. That would trigger the revert path. For the second path, this is the safe execution path through the contracts. Since we have two symbolic transactions, we'll generate two concrete transactions. The values are not constrained, and so anything goes for them, as we can see here. For the data must start with wheat for both of them. And for the second transaction, we constrain that the first argument must be less than 42. And so, for example, the solver might give us 41. Lastly, to actually trigger the potentially overflowing path, it'll look very similar to the last slide, but the values are unconstrained. The first 4 bytes of the data are constrained, and the first argument needs to be greater than or equal to 42. And so anything that fits that would work, for example, 43. And then, so that's how we start from these just abstract path constraints and bring them into actual concrete transactions that you can launch on the blockchain to basically force the contract into a certain state that was found by the analysis. Lastly, so how does this result in being able to check for failure states in the contract? So I'll break this down into 2 categories. You can have assertion failures and proper like security bug failures like integer overflows. And so for assertions, these are, get these for free basically because assertions are simply conditional branches in the code that just lead to a revert. These branches are not special, and so they'll be discovered just like any branch in the program by symbolic execution. And if those particular paths are satisfiable and able to be solved for, Manticore will generate an input that can trigger it and lead to a throw exception. And the presence or the existence of that input proves that the assertion can fail. Likewise, if the engine did not generate an input down that path, that proves that it's not possible for that assertion to fail due to the fundamental nature of the analysis. So for security issues like integer overflows or unchecked external calls and things of that nature, we use Manticore's instrumentation features to implement analysis modules for them. And so Manticore is highly instrumentable, if that's a word, and you can develop plugins to detect dangerous behaviors. For example, we have one right now that is just kind of a proof of concept, but checks at every addition or subtraction. Is it possible? It asks the solver if it's possible if the operands in that instruction could lead to an overflow, and you can alert it on that way. But these plugins run on all paths that the engine finds, and therefore checks every path if it can integer overflow, basically. So that pretty much wraps it up here, but the takeaways are that symbolic execution is very cool and is especially useful for Ethereum security. Manticore is a tool that lets you take advantage of it. And so now I'm going to do a little demo I can take some questions and we can wrap it up. So this is the same contract I showed on the slides. It has the test me function with the integer overflow and that check. And we'll just give this contract to Manticore. So what I'm demoing here is just Manticore is out of the box symbolic execution capabilities. And so you don't particularly have to know anything about Ethereum or security to use it. You just press enter. And so it compiles that contract and starts its analysis. It's going to output a bunch of stuff, and I'll talk through it when it's done in a couple of seconds. Okay, great. So starting from the top. Manticore just calls into Sol-C to get the bytecode, and so that's what this output is from at the top. And then this chunk right here is Manticore executing its first symbolic transaction. And so we can see it finds a number of states, including 1 stop, 2 reverts, and 1 not enough funds. So my diagram earlier was a little bit of a simplification in terms of all the states that can be found. In reality, there's a lot of other checks that exist in the bytecode to implement things like checking if the function was payable or not. One of these reverts is going to be for checking that function identifier. There's also this implicit fork of if your transaction had tried to spend more than the balance, since remember we used a symbolic value. But this stop state is what's important. This is the state corresponding to it successfully finding that function and executing it through once, setting the did init flag to 1. So at this point, it checks that the coverage is not 100%, and so it goes and submits another transaction to continue exploring state. That's what this second group shows. And so again, find some identical states to the first one. But importantly, here, maybe you can't see that, there's 2 stop states now. And so what happened is that first stop state executed through the contract again and found those 2 other states at the bottom of the function. One of those corresponds to the overflow, and so our instrumentation plugin detected that and saved that for later. At this point, it detected that it reached 100% code coverage of the function and then killed the 2 alive states, generating test cases for them, and then reported its findings. And so it reported that it found an integer overflow at an add instruction at this contract address, and even correlates it back to this line of solidity. There's one more thing to show you. So Manticore creates a workspace directory for every analysis that it does. And if we take a look inside, we can see all these files, test 0, 1, 2, 3. These all correspond to the various states that Manticore discovered. Probably the most interesting of these files are these .tx .number files. So these files contain the concretized transactions that you can actually use to launch on the blockchain. And so let's just check them out. Test 6 and 7 were the 2 inputs at the end that triggered the safe path and the overflow. So if you just look at these transactions, transaction 0 is the transaction for creating the contract initially. Transaction 1 is the transaction that just executed regularly. And so the value doesn't matter here. We can see that it solved for the correct hash. Not hash, but I guess it is a hash, but the function identifier. It's CC 2761, something like that. If we go over to Binary Ninja, we can see, I can't zoom in very far, but that's what it says right there, CC 27. Let me do that. Thanks, Jordan. Go with 30. Nice. So CC2761, that's the hash to get to the function. And so that's exactly what we see right here. And lastly, transaction 2 is what is going to trigger the overflow. And so this array is the arguments that are provided to the function. That looks bigger than 42. So that'll work. Cool. That's pretty much it for my demo. I'll be happy to take any questions at this point. Thanks a lot, by the way.
Got time for 2 quick questions.
They're in the front.
Can Manticore handle external contract calls?
Yes. Not with that one-click interface, but Manticore has a more sophisticated API where you can completely customize a blockchain state, essentially. You can set up multiple contract accounts, configure them to trigger each other and stuff like that. And so you can, using the API, emulate much more complex attack scenarios.
That works out of the box online with docs?
Not right now,
Okay.
but it will soon.
Cool.
Over there.
You mentioned all the integers are. You mentioned all the integers are 32 bits or bytes wide. When you actually go into doing solving and stuff with your Z3 or whatever engine, do you find that the added complexity of having to solve for all those bytes adds runtime overhead, or is it relatively straightforward still?
I haven't tested it enough to really know how to answer that yet, so I'm not sure.
Cool.
They're in the back.
Whoa, all right.
Great work, and thanks for open sourcing it. I noticed in your diagram, the initial state and also the transactions are using concrete values, like the transaction destination and source. Is it possible to make the initial state symbolic or the source or destination of the transaction symbolic?
Yes, that same kind of thing with the previous question. If you wanted to use the API, you could do that too. Making the address symbolic would be kind of interesting. But yeah, you can.
Okay, I think that's all we got.
Okay, thanks a lot. You can find Manticore online. The functionality I demoed is not available online right now, but it will be quite soon.
Install from master.
Yeah, that's right. Thanks, Dan.